Hello everyone, we'll continue with the topic of moment of inertia only in this video also, and we'll talk about one theorem first. It's called parallel axis theorem. Let's see what is that. Parallel axis theorem, and that is a very important theorem in the topic of rotational motion, because that will help us to find out, if we know about the center point, what is the moment of inertia of a particular object, we can find out what will be the moment of inertia with respect to another axis or another point. Let's see. Suppose this is a uniform rod which is having mass m and the length is L, and center of mass is at the middle point of the rod, because this rod is uniform rod. So this is the axis. Suppose we are interested to find out what will be the value of the moment of inertia or the rotational property of this rod with respect to its center of mass or the axis passing through the center of mass. Let's say it is z axis. So maybe we can imagine this marker as this rod and center of mass maybe at the middle. We are interested about this property, this rotational property of the marker of the rod, right? Okay. And parallel axis theorem says that if we know what is the rotational property or the moment of inertia with respect to the center of mass, if we know it, then we'll be able to find out with respect to another axis, which is then going to be the axis of rotation, we'll be able to find out the moment of inertia with respect to that axis also. Suppose the axis of rotation is shifted by d distance from the center of mass. So initially it was rotating like this, and right now the axis is shifted from here, middle point, to here. So right now we are interested about the rotational property with respect to this point. So it says that if Iz dash is the moment of inertia with respect to the new axis which is shifted from the center of mass by d distance, the Iz dash or the new moment of inertia with respect to the new axis, it will be I center of mass plus the mass into the distance square. The distance is shifted from the center of mass. So this is the parallel axis theorem, and this is very important theorem. Now in the last video we have found out the moment of inertia of a rod with respect to one extreme end. Rod length is L, mass is m. We have found out that, okay, about this extreme end, if the axis is passing with respect to this axis like this property is m L square by 3. That is I z dash in this example. So with respect to the center of mass or the middle point, we do not know what is the moment of inertia. We can find out using that theorem. Let's see. Now from the center of mass, axis is shifted by L by 2, then only we will be able to go to the extreme point, and then only we will be able to find out what is the rotational property with respect to the one extreme end. Now in this case, D is L by 2 and Iz dash we know, that is ml square by 3 with respect to one extreme end axis, that is ICOM plus m into L by 2 square, because from the center of mass axis is shifted by L by 2 amount. Now what is ICOM or moment of inertia of the rod with respect to the middle point? ml square by 3 minus ml square by 4. So it is becoming ml square by 12. So for a uniform rod, right now we found out that the moment of inertia with respect to the middle point is ml square by 12 ICOM. That is the usage of this parallel axis theorem. This is one of the usages. Now we can discuss about more examples. Now let's try to validate the parallel axis theorem with this example, where two particle mass m are connected by one massless rod. The length of the massless rod is L, and with respect to the middle point, what is the moment of inertia? Iz. Individually, what is the distance of these masses from the center? L by 2. This is also L by 2. In the last video, we have found out the value of Iz with respect to the middle point. We'll just do the summation of the multiplication of mass by the respective distances square from the axis of rotation, plus m L by 2 square. So this m is located at L by 2 distance from the center, and this m is also located at L by 2 distance from the center. So mass into distance square plus mass into distance square, that is the moment of inertia with respect to the middle point or the z axis in this case. So what is the answer? M L square by 4 plus m L square by 4, that is m L square by 2 Iz with respect to the center of mass. Now if I tell that I am not interested about the moment of inertia with respect to the center of mass, rather I am interested about the moment of inertia, the rotational property with respect to one extreme end, then what will be the value of Iz dash? See, this mass is located at how much distance from the axis of rotation? Z dash L, m into L square, plus this mass into that distance square. This mass, the distance is 0 because the axis is passing through it, so 0. So it is becoming m L square only, Iz dash. That we got already. Now let us try to validate. What parallel axis theorem says? If we know ICOM, then we can find out what is the value of the moment of inertia with respect to another axis that is shifted by some amount. So ICOM you already know, ml square by 2. Now initially, if you are interested in this rotational property of the axis which is passing through the center of mass, this moment of inertia is ml square by 2. You found it already. Now what is going to be Iz dash? ml square by 2 plus total how much mass is there? 2m mass is there. Is shifted by how much amount? L by 2 amount. So L by 2 square. Parallel axis theorem means center of mass plus total mass into the distance square the axis is shifted. So if I am interested about this axis, it is shifted to this point, and this point is L by 2 distance from the center of mass. So we can find out ml square by 2 plus total mass into the distance square is shifted L square by 4. See, it is becoming ml square by 2 plus ml square by 2, that is becoming ml square. So see, it is same. So parallel axis theorem is validated with this simple example only. Now let us proceed to find the moment of inertia of a ring mass. Suppose this is a ring, the mass of the ring is m and the radius of the ring is r, and I am interested if this ring is rotated with respect to the center. This ring is rotated like this, so the axis of rotation is upward. So let's say this is z axis. Now what will be the moment of inertia with respect to the z axis? Iz, how much? So see, this is a continuous system, or mass is uniformly distributed over this circular ring. So we can imagine that small masses are there. Small masses dm, dm, dm. Here also dm. The small masses constitute the total mass capital M. So for one small mass, if we take dm, it is located at how much distance from the center of rotation? R distance. So small moment of inertia di for the dm mass will become dm into r square, mass into the distance square. Now similarly, If you are interested about dm mass here, this is also at distance r from the axis of rotation. So I have to again add up all this moment of inertia. That means I have to take a summation of all this moment of inertia of small masses, and that will constitute eventually a big mass m. So that means I have to do the summation. Small di mass. I do summation. So this is often called integration. Integration of dm into r square. I am doing the summation for all small masses. Now see, for this all small masses, all are located at distance r from the axis of rotation. So r is constant for all the masses. So that will come out of the integration. So r square integration of dm, that will constitute eventually total moment of inertia I. Now what is the summation of all the masses? If I do the summation of all the masses, it will constitute one big mass. So integration of dm is m only, r square into m. So we can write that Iz is m into r square. So for a ring having mass m and radius r, the moment of inertia with respect to the z axis or the axis which is passing perpendicular to the plane it is creating and which is passing through the center of mass also, the moment of inertia is m into r square. Now with the idea of the moment of inertia of the ring only, you will be able to tell at least the minimum idea of what will be the moment of inertia of a disk having the same mass m and the radius of r. So disk means it constitutes many small rings like this with increasing radius. So moment of inertia for one small ring, you know, that is m into r square. But here see, the mass distribution is not even. Rather, this disk constituted of many small rings of varying radius starting from 0 ending at r. So mass is not entirely at the r distance from the center of rotation. Rather, some masses are there which is at r equal to 0, some masses are there which is at r equal to ry 3, some masses are there which are having distance r by 2. So mass is distributed. So moment of inertia will be less than mr square, of course, because the mass is distributed towards the center also. The more the distance of the mass from the axis of rotation, more the moment of inertia is. If more mass is concentrated towards the center of rotation, the moment of inertia will be less. Now let's look at this disk from the top. So Z is outward. I am looking at the disk from the top. Now see, I imagine one small ring which is having thickness of dr, small ring. At distance r, I am thinking about one small ring which is having the thickness dr. And this r will vary from 0 to capital R. From 0 to capital R it will vary. Now I am imagining a generalized ring which is at distance small r, and I am imagining a ring of thickness dr, small. So this ring is having some mass. Now what is the area of the ring? See, dr is the thickness, and you know the perimeter of this ring, that is 2 pi r. If you unfold it, this ring, and keep it like this, the thickness is dr, length is 2 pi r. So what is the area? 2 pi r into dr, that is the area of the small ring. Now total mass of the disk is given as capital M. Now this area you know of the ring. Now what will be the mass? If pi r square, if the area, then mass of the disk is capital M. If 2 pi r dr is the area, then what will be the mass of this ring? M by pi r square into 2 pi r dr. Then this is becoming 2m r dr by r square. That is the small mass of the ring. Although that is also called the differential mass of the ring. Now you know the small mass of the ring, or the mass of the ring, you know, dm. It is located at a distance how much from the axis of rotation r. Then what is the moment of inertia of this ring? Small moment of inertia, dm into r square. Then the ring moment of inertia. Now dm you just put it, 2m r dr by capital R square into r square. That is the moment of inertia of the small ring we are considering, differential ring we are considering. Now this disk is constituted of many small rings, so we have to do the summation of the moment of inertia of those small individual rings, like this, from starting from r equal to 0 ends with r equal to capital R. So extensive way of doing summation is integration. If you want to find out the entire moment of inertia, I have to do the summation of this all small moment of inertias, and we will eventually get the moment of inertia of the disk. 2m is becoming r cube dr by capital R square integration, and small r is varying from r equal to 0 to capital R. Now see, these are all constants. Capital M, R is constant for a particular disk. So this will come out of the integration. It is becoming 2m by r square integration of r cube dr 0 to r is the limit. The integration of r cube dr is r to the power 4 by 4 outside 2m by r square. Limit will put 0 to r. Then we are getting 2m by r square r to the power 4 by 4. So that is eventually becoming m r square by 2. So moment of inertia of a disk having mass m and radius r is Iz with respect to the center m r square by 2. Now see, if I tell you the ring is having mass m and radius r, it is having moment of inertia m r square. Now for a disk having the same mass m and the radius r, outer radius r, the moment of inertia is m r square by 2. The moment of inertia is m r square by 2. Why is that? Because moment of inertia depends upon the distribution of the masses. If more mass is distributed away from the axis of rotation, the moment of inertia will be high. So entire mass of the ring is located at distance capital R from the axis. So more mass is distributed away from the center of rotation. But for in the case of disk having the same mass, some masses are distributed towards the center also. So moment of inertia will be less compared to the ring. That is why it is becoming less than the ring, m r square by 2.